for member BC. If I can put it in different place, maybe that will be easier to see that. Suppose I put it like this. To balance the application of M moment MB, the direction of the shear force to member BC must be up or down. It must be up. Because this shear force for BC will produce the moment in this direction. And that will balance MB. Right? So that's how we conclude that the shear for member BC is not downward pointing, but it's upward pointing. Which is here. It's the same reason how we decide that the direction of VA is pointing to the right. Now, if the shear force at MB, of course, this is what we're going to call another force. Now, what will be the force acting at the B end, which is here? You know, this force will have to be balanced to here and pass to here. So what's the force that we're going to find it at the B end of member AB?
Downward P.
It should be downward, right? So you should have another downward force here. Now, if you look at the joint, you have the force P here. What happens to your force? So at one end, it's upward pointing. That is coming from member BC. Goes like this, right? So in order to balance it, it will generate a force like this and pass to another one like this. Correct? Because they have to cancel out in pairs. Because they are internal. Now, from here, the application of this moment will produce an internal moment MB. And this MB, do you think is helping the rigid frame to against the application of the force P, or is the other way around? What do you think?
I think it's amplifying.
It's amplifying, or does it amplify the resistance of the rigid frame, or does it reduce the resistance of rigid frame? Does it help or does it not help? Remember that the direction of this green color shear forces or internal, let's call them forces because to columns they are axial force, to beams they are shear. So just call them green forces. These green couple forces, they have this direction because of the direction of this internal moment, MB. So when the internal MB goes in this way, you can see that at this joint, it actually produces a reaction against in the direction. With the axial force. Here, right? So what does that mean? That means for this kind of loading, it actually reduces the buckling capacity of column MB, because the moment produces another force that is in the same direction with the external force P. So you will look at this part and to make that judgment right here. Why? Because what if we change the direction of MB? If MB is in the opposite direction, suppose MB is in this direction. If we call it MB prime, right? Now what happens to the axial force on the member AB? You flip the direction, the orientation of MB, certainly the correspondingly produced internal force will be in the opposite direction. That means this will become this. So you can see that the direction of the internal moment actually can affect the buckling capacity of the column member AB here in this analysis. Now, and once we figure out these, in fact, we actually know the values for VA. The value of VA is just MB divided by the length. The length is LC. So we actually know this value already. We know that VA is actually MB over LC. It's moment divided by the distance. And then we can start putting all this in the force equilibrium. So for the next step, what we're going to do in step 2, this is step 2, right? Step 2 is to develop the moment equilibrium. Summation of moment to be 0. So we're going to take the moment equilibrium at point B. If we can start doing it. MB to be 0, and you can define whichever direction you want to use. And suppose we look at the column member first. We take the moment equilibrium at B, but it's at the B end, which is here. And by assuming clockwise or counterclockwise, actually, either way is fine. Suppose we assume the counterclockwise, the clockwise direction is a positive direction. Then you come back here. You have MB in the clockwise direction, so it's positive. And the VA, that means here. This is the M internal. For the force, I think that I need to show this part so you know that which point that we are looking at. We are looking at here, which has the forces here. They have this is MB, this is VA, and we are looking at the internal moment at right here. So our internal moment is going to go like this. So that's the internal moment here, because we are cutting a section and looking at what is internal moment in this column, and as we did before. And of course, the force equilibrium suggests that inside here, you must have the same force that we considered before. And the force that we have here is P plus this vertical force. And this vertical force has a value of MB divided by LB. So this one here is MB divided by LB. It's different from this one here. It's MB divided by LC. So that means the force acting here is going to be P plus MB divided by LB, because that's the summation of these two. So that means this force here is going to be P plus MB divided by LB. And of course, if you have a VA acting at the B end of member AB, you must have another internal shear acting in the opposite direction. That means there must be another shear force acting here, and this must be VA. Then you can take the moment equilibrium at this point. So if we take, this is actually how we look at the M internal. So if the clockwise direction is positive, and this internal moment, of course, will have to be what? Will have to be negative, right? So you have to be negative M internal. And for the moment produced by this P and plus MB divided by LB, is positive or negative? It's also negative. So it's going to be negative.
Should M internal be positive? You've drawn?
Yes, it actually should be positive. Thank you, because we assume positive direction is clockwise, and this M internal is producing positive. Thank you. So this is MB plus P plus MB divided by LB times the distance is Y now plus MB must be 0. Because MB is in clockwise direction.
What about VA?
VA,
Should there be a negative VAX?
do we have VA here? Do we have shear force here? Because the shear force, when there's a shear force presence in any beam or any column members, that means the change of moment, right? When you have shear force, that means the moment is changing. Now in this case, if we look at this member here, they will only have shear force at point A, and between points A and B in member AB, there's no any other forces here. That means this bending is merely due to the application of the force P, and the P produces internal moment MB.